Oh, yes. So, how's the assignment going? Everyone happy with it? Excited? Yeah, not too much. Okay. So, first observation, I don't know if it's on an oversight on my side or on you guys' side. I think it was clear, so I didn't really pay that much attention to it. But what is definite integral of a to a of f of x dx? What is this equal to? Okay, it's equal to 0. I didn't specifically write that out. I don't know if it's my bad, but I just thought, hey, the kids are just gonna apply the definition, right? What's the definition to this? What's the definition? Just big f of a minus big f of a, right? Which is equal to 0. And then I thought, hey, maybe that doesn't work. Maybe they're not gonna think of that. I defined the definite integral as the area under the graph. Remember, this is a, b, this is my f of x, and I defined the integral as being, this thing, integral a to b of f of x dx. Right? This is one other definition that I use. Now, if if I have from a to a, I just have one line, so 0. So yeah, just because I didn't integral of a to a of f of x dx is equal to 0. Okay, now I just wanted to clarify that since I saw some that some people were confused about it. Now, another thing which I really wanted to talk about, and I'm kind of lacking right now. Oh yeah, don't hate me. The first 3 problems have nothing to do with computing integrals. Okay, the first 3 problems, it says there specifically, I recommended writing it in bold after every question. Do not attempt to compute the integral. You're not gonna solve that. Okay. Now, somebody overheard me. I think in one of the previous seminars, I do tend to speak loud, so I would rather just make it, I guess, available to everyone. I don't know. It started from a joke, but it ended up being pretty serious. If you can solve a random integral or limit problem faster than I can, I will automatically pass you on the assignment. Okay. I got challenged. I think it was they decided to do 2 problems against me. So if anyone, I don't want to discriminate. If everyone wants to do that, we can just take an exam problem. If you solve it faster than I do, I'm just gonna pass it. I'm just gonna pass you on this assignment. So yeah. No, it really happened. So it's not funny. It's actually happened. So yeah, awaiting challenges, I guess. Cool. Now, in terms of integrals, we are mostly done. Okay, we are kind of done with everything. All I can do is just exercises, and I guess I'll give you some computational tricks which I saw most of you are not really familiar with. So here's one that's really strong. I was surprised you don't know. It's this one. What is I don't know. Let's put. What is 3 over x minus 2 x plus 1 equal to? Say I give you this integral. 3 x minus 2 x plus 1 to integrate from 5 to 10 dx. What is this equal to? And now, maybe you can do it for substitution. Yeah, maybe. But the easiest way to do this type of problems is to apply the formula, which I found out not a lot of you know. This fraction, 3 x minus 2 x plus 1 is equal to 1 x minus 2 minus 1 x plus 1. Okay. Fast check. We bring everything to the same denominator. So I have x plus 1, x minus 2, x plus 1, minus x minus 2, x minus 2, x plus 1, x plus 1 minus x plus 2, x minus 2, x plus 1. Fair, we got the same answer. This is really, really strong. Why? Because if you attempted to solve this thing by substitution, I'm trying to think exactly how you solve this, so give me a second. I would say it's probably going to take you 1 page and something to show it. And that's my writing. So I would definitely rather recommend doing it that way. On the other hand, if you use this theorem, what do you get? Well, let's use another paper. If you use that theorem, you get integral of 5, 10, 3x minus 2, x plus 1 dx is equal to integral 5, 10, 1, x minus 2 minus 1, x plus 1 dx. Okay? Why is this good? Because now I can just split it and I get 5, 10, 1 x minus 2 dx plus integral 5, 10, 1 x plus 1 dx. And what's the good part about these 1 over x? They get transformed to log of x. Okay, all of them. So I just get log of x minus 2, 5 to 10, plus log x plus 1, 5 to 10. Okay, so really, really simple. Now, really simple if you know the formula. If you don't know the formula, it's messed up. So the general formula that you can use for this type of fractions, whenever you see this grouping, this type of x minus something times x plus something, the formula is this. If you have constants, let's just say constants a and b, and you have a plus b constants, x minus a, x plus b, let's just put a b positive, although it doesn't matter, but for being simpler, x minus a minus 1 x plus b. Okay, really, really helpful formula. As you probably noticed, I mean, you can try and solve that this other way. Again, I think it's going to take a little bit of time. Cool. I wanted to show you this thing. Then I wanted to show you, to emphasize again the importance when computing limits. And I think, and again, I think Shalarnik went over this, but I don't think he emphasized that much. You've all seen this operation of, you know, I think he said, he called it dividing by the strongest power. I think something like that. Okay, before we get that, I'll write it again because some people forget. The only guiding idea that should be in your solving of limits is always evaluate your limit. Always know exactly where you are. Split it, evaluate it, always, always, always. Because I can't say like how many mistakes I always see and how many mistakes I am going to see on the exam because of this. Okay, just evaluate, know where you are. I see that a lot of people are making progress and they're actually evaluating, but a lot of people aren't. So, you know, this is the idea, is that if you have a strong mentality of evaluating your limits and you know, okay, I need to evaluate, I need to write my thing in a way that allows me to evaluate it, the solution just comes naturally. If you don't have this strong impulse to evaluate, then you're going to get stuck eventually and you're going to panic. Okay? Now, I'm going to generalize basically his idea, one of his ideas. One of his ideas was, okay, if I have x to the 4th plus x2 plus 1, 5x third plus 27x. Limit x goes to infinity. Okay, we had this thing, and he basically said, okay, let's just divide by the highest power. So that's x to the fourth. And I get limit x infinity, and you get, again, all these powers. You get x to the 0, x minus 2, x minus 4, 5, x minus 1, 27, x minus 3. Okay? And this allows you to evaluate it easier because you're going to get this goes to 0, this goes to 0, this 0, this 0, and this is 1. Okay, so you get 1 over 0, which just gives you infinity. Pretty neat, pretty simple. Now, why did you do this? Because you know, you had here, if you were trying to evaluate it from the start, you had infinity, 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 infinity. And note that here you could apply L'Hopital because you have an infinity over an infinity case. So you could have applied L'Hopital if you didn't want to divide by x to the 4th. Now, in some cases, just purely applying L'Hopital, it's not necessarily going to work, or it's going to be really, really complicated. What is the only result that I have specifically told you to memorize or, you know, understand, but I've told you to memorize in the limits case? Although I'm not teaching limits, apparently I'm doing a little bit of it. So what is the only result that I told you? I told you to memorize that exponential of x much, much bigger any power function. Yeah. This is, I've specifically told you to memorize this every time and use it anytime you can, because it's just so strong. It simplifies, and it's like a cheat sheet, a cheat code. For example, if you're writing somewhere on the exam and you get stuck and you have no idea what to do, but you just see an exponential there, you can just be like, oh, exponential is much bigger than anything else. And that could basically just save you and give you a full score, or, you know, solve the limit without actually doing the work. I can't emphasize how strong this is. Now, what the problem with this is, obviously, if your limits look something like this, x infinity, some x to the power of 247 here, I don't know, plus etc., over x to, again, another power, 2022, because I thought it's pretty standard, something like that. Then if your limit looks something like this, automatically you can just say exponential bigger than power function and you're done. Okay, this is equal to infinity because exponential bigger than power function. My question is, what happens when you have something like this? E to the x. Let me think about it for a second. X squared minus ex log of x 247, something like that. I don't know. Okay, 47 x 2022. Kind of like that number. Okay, cool. So we have this one. What is the problem with this? Well, we start with the only thing we know how to do, which is evaluate. We evaluate this. When x goes to infinity, this goes to infinity. Okay, clearly. So this whole thing goes to infinity. Now, up top, e to the x goes to infinity. This goes to infinity, infinity, infinity. Okay. Now, you have up top an infinity over infinity case. At this point, you cannot apply L'Hopital. Okay. This is infinity minus infinity over infinity case. No L'Hopital. Okay. Wrong. You don't know what infinity over infinity is. Oh, infinity minus infinity is. You don't know what that is. This is your problem. So now, a good student just basically said, that's fine. I'm just going to create a fraction and evaluate this up top. And maybe in some cases you're going to get a result. In some cases you might not get the result. What is the problem in this case? Why doesn't your only argument that you know in this class e to the x stronger than any power function work in this case? Because, and I'm going to use some really smart terms, so be careful. Because this is e to the x infinity, and this is, again, e to the x infinity. Okay? If I had something like polynomial here or something like that, maybe we could make it work. But in this case, it's not okay. So a strategy is, there are two possibilities here, whichever you want. They're both like not isomorphic, and the same. Yep. That is the first solution, yes. The fourth solution to this type of problems is factorize e to the x. Okay? Why is this a good idea? Because let's use my case, which is really thoughtful. Okay? Why does this writing make sense? Because the idea is that this e to the x is the dominant power. Okay, it's the thing that's going to dictate where my limit goes. Okay, this is much bigger than this thing. Exponential is much bigger than what's underneath. So what's going to dictate where my function goes is this parentheses. Do you understand the logic? Like, what I'm saying is, by doing this writing, I'm basically saying, if this thing up top is a minus, then I am going to get minus infinity. If this thing up top is a plus, I'm going to get plus infinity. Make sense? So again, I can just write it as limit x infinity e to the x. Let's split it like that. Okay. Now, the idea is that this thing is always going to be infinity because exponential much bigger than power function. Exponential much bigger than power function. And now you're basically just stuck to see what this is. In the unfortunate case that is a zero, that we're going to have the conversation some other time. Because we need to do something else if this parenthesis is a zero. But in my case here, this parenthesis is going to be minus infinity, of course, because although this is infinity and this is again infinity, this x to the 247 is much bigger than x squared. I hope I don't need to convince you on that. Okay, so this is minus infinity. Infinity times minus infinity is minus infinity. So factorization is really strong. Now, I said I'm going to generalize his method, which is dividing by the strongest thing. So another solution which you can do, and I personally prefer it because it's much cleaner than this, is dividing the fraction by e to the power of x. So my fraction was initially 1 ex, limit when x goes to infinity, ex, x squared, log of x, x247, 47, x 20, 22. Okay, now remember, his method, or the professor's method, Shilara's method, was to basically divide by the strongest power, right? Let's go back to our example. Our greatest power here was x to the fourth. This is obviously the biggest term, so that's going to dictate where we go. So that's why I divided by it and got the result. Okay with that? Now, the general method is to divide by the biggest thing at the biggest thing. And I know that sounds really mathematical. Let me explain. I see this. Oh, there's supposed to be an e of x here. I see this e of x here, this e of x here. Those are that's by far the strongest thing I have in this fraction. Okay? Everything else is a power function. Remember, exponential bigger than everything else. So what I'm going to do here is I'm just going to divide everything by e to the power of x. Okay? And I get limit x infinity, x squared, minus log x, x247, 47 x222 over e to the x. The result obviously is the same as the factorization above. I just prefer this one because I believe it just looks nicer and it's simpler to understand. Obviously, this is a simple example that I took right now. I just created it. But obviously, we can have more complicated things. I just prefer this one. Now, the idea is the same. This thing over here is 0 because exponential, bigger power. And here up top, I have left, x247 is bigger than x2. So this is just minus infinity over 0 minus infinity. Okay. So what I'm telling you, what I added is if you see an e to the x, always think how to, make it shine if it makes sense, because that is the strongest thing. That's going to dictate where your limit goes. The others don't matter. Okay. Think of it as e of the x, think of it as the present prime minister, and the other as just the peasant. They don't matter. Unfortunately, that's a real life example. But just focus on e to the x. That's the strongest thing you're going to encounter. Yeah, so this is what I wanted to show you about limits. Now I could do like an example of another, let's get back to our things, which are integrals. And I could do an example, I guess, with integrals. Let's see. Should we take another exam problem? Do you guys want to do that? I think I did it in one of the seminars. I could do an exam problem because I can cherry pick, but eventually you're gonna say, hey, they look kind of simple. So yeah. So let me just search for one right now. We're gonna choose it semi-randomly. If I think I have an idea how to solve it, we're gonna do it. Otherwise, we're gonna pretend that it's not what you guys need. So hopefully I know how to solve it. Previous exams, I don't know, 2019 sounds kind of hard, but let's see. Yeah. Okay, where'd the limit at? Oh, that's actually good, actually. I like it. Okay, this is not bad. We're gonna compute this one. We're gonna do point C here. Okay, I think this is a good example. It uses substitution, it uses limits, it uses everything. It's like a full workout kind of thing. So ln of z, and you have integral from 1 to infinity, ln of z, z 3 over 2, d of z. This is a simple problem because it tells you what substitution to use. I think it would have been more interesting if they didn't tell you and they just gave you another factor or two. I'll show you. I didn't write anything. I just copied the problem. No, I mean, I'm going to show you what I wrote. I just copied the problem. Okay, so this is what we need to solve. This is partially cheating because, again, they tell us what substitution to use. But I believe that you guys could solve it no problem. Okay, now, where are we at? 1 second. No, this is not good because I can just solve it. I don't need to solve the integral because, yeah, this is not going to work out. Let me adapt to the second so we actually solve the integral. No, this is too easy for you guys, really. Okay, I'll give you 5 minutes. No, okay, I'll simplify it for you guys. Okay, just do this. I will give you 5 minutes to solve this one. Again, your integral 1 infinity log of z over z d of z. I'll give you 1 minute to solve this. I mean 5 minutes, sorry, 1 minute, maybe 2. So again, the problem tells you to use the substitution, u is equal to log of z. After you copy it, I'll look for something more challenging for you guys. Oh. Okay. How's it going, guys? Did we manage to do it? Hopefully, ideas. Well, I would say, given, if I gave you this thing alone, I would say, might be a little bit harder, let's say. If I tell you what substitution to use, again, as I said, in by parts and in substitution, the whole key, the whole hardest part is making this choice. Once they give you this choice, you should be able to do it. So I'm just gonna do it myself. U is equal to ln of z. Du is equal to 1 over z dz. If z goes to 1, ln of z is ln of 1, which is 0, which is equal to u. And then if z goes to infinity, ln of z goes to infinity as well. So u goes to infinity. Okay, I did all my substitution things. Remember, I did my substitution, my du, and my heads of integration because it's whatever. So, because it's a definite integral. So from here, I get integral 1 from 0. Again, I have to change this. 0 here. Infinity of log of z becomes u. And then I have 1 z dz. Okay? What is 1 z dz? It's just du. Okay, it just magically becomes du. So this is just integral from 0 to infinity of u du. Okay? And this is just, remember, this is just u squared over 2 from 0 to infinity. And here's the problem. Remember, I told you that infinity is not a number. So how do we deal with this? We just write it as limit when a goes to infinity of 0 to a of u du, which is just limit when a goes to infinity of u squared over 2 from 0 to a, which is just equal to limit when a goes to infinity of a squared over 2 minus 0. So just limit when a goes to infinity, a squared over 2. This is just infinity. Everyone on board with it? Any questions on what I did? Be honest, how many of you did it? Raise of hands. Okay. Okay. I should have like the whole min thing, whatever it's called, but I always forget. Asking you what went wrong. What's the thing called where you put questions out? The one we used, the Shalana was using? Mint? Okay, I'll just write it. And I'll ask the question because it's quite curious. Okay, what was the problem here? Anyway, luckily for you, I knew this was too easy. So I found some other problems. Note, like let's do part B here. Okay, we're gonna do problem B. I mean 2B from this exam, 2018 exam. Yeah. Please notice that it says here show by antiderivative. If you were to take a derivative, you would get 0 points. Yeah. If the problem does not specifically tell you to compute something by integration or antiderivative, you are free to just take a derivative the right hand side and show that it's equal to the left hand side. But if they show by integration or antiderivative, just do the integration. Okay. So if they didn't say that, show by antiderivative in part in B, I could just, let me copy it first. So x1, 1u, 1 ln of u, du is equal to ln 1 minus ln of x. Okay, and then it would be, the second part would be this thing. This is easy. Okay, so these are the equations. Note again, especially in the indefinite one, if they didn't show me, and they didn't ask me to show by antiderivation, I could just take a derivative of this whole thing and show that it's equal to the thing under the integral. Right? Remember our definition. Our definition was that integral f of x dx is equal to big F of x plus a constant if and only if derivative of big F of x dx is equal to small f of x. This was the definition. So if they didn't tell you specifically, I could take a derivative of this and check if it's equal to what's underneath the square, the integral. Make sense what I'm saying here? Luckily for you, it got changed. Now you can't do that anymore. So let's try and compute point I. And I don't need you to write the whole thing, the whole explanation, the whole proof. I will give you, on the other hand, 1u, 1 minus ln of u. du. Solve this. I will give you like 2 minutes not to write anything. I'm not interested in the writing because I'm going to write it anyway, but to think of the substitution. What substitution would you use here? Or what by parts would you use here? You know, just challenge yourself. What would you, if you saw this on the exam, instead of screaming and panicking, what would you do to this one? Okay, just think about it for like 2 minutes. What change would you do? I don't know. How would you play with the fraction? Okay, this is all integrals. The only hard step on integrals is the one you do in the first 5 minutes. After that, it's just simple computation. If you do this correct step in the first 5 minutes, then you're gonna get maximum points on the problem. So just think, what would you do in this case? What would you replace? No, x is just a number. This is a way of the professor or problem, whatever, to mess up with you. This x here, we got a question about this x here. Okay. Do you see any other x anywhere in this integral? No. What is usually in the heads of integration? Just some numbers, some constants, right? Remember, we had integral from 5 to 10, 0 to 100, whatever. So in this case, he's just trying to panic you, whatever. This x is just a number. Usually, and I put emphasis on here on this when I taught you, but I'm going to say it again. This du, the thing that's next to this du, tells you what you're integrating over. This thing tells you what the variable is. Okay. Okay, any ideas? Any ideas of how to solve it? Yeah. Fair? Why? Okay, so that is the smart answer. Okay, he's right. That's exactly what we're gonna do, and that's correct, and we're gonna get the correct answer. The reasoning he used was a smart reasoning. The reasoning I would use, because I'm not as smart, I would say, I'm just gonna use the substitution on whatever the ugliest variable is there. I just want to get rid of it. Okay. So what's the ugliest thing? Clearly log. I told you, like ever since we started, log is when you're doing integrals of log, it's something really, really nasty to work with. You don't want to work with that. Okay. So that's where the idea comes from. I'll just take this log of u as being my variable, my change of variables. Okay, makes sense. I'm just looking what I want to get rid of. Do you want to do computation with log of u integral? No, I'll show you maybe. I don't know if we have some time. How does the integral of log of t looks like? And maybe at that point you're gonna stop wanting to do that to yourselves. So again, the idea here is this log of u is ugly. It's 1 over. It's the most horrible thing. You want to get rid of it. So you make that your v. Now, you can have, there are multiple changes. It doesn't matter. They all get the same result. You can have 1 minus log of u is equal to v, which was his solution. And it's, I guess, you want to simplify your life as much as possible. That's perfectly fine. Or if you're just like more dumb like me, you can just say log of u is equal to v. This is again works perfectly. Okay. To be honest, I didn't even think of 1 over 1 minus log of u. I just thought of this one. Okay. Usually, when you're dealing with substitution, replacing the ugliest thing there is going to give you the correct solution. Okay. Don't quote me on that because that is completely informal, but it just works. Okay. I don't have an explanation. It just usually works. So we do this substitution again. I'm going to do my substitution because I'm afraid I'm going to mess up the other. So let's do this one. But again, his idea works just as fine, if not better than mine. Okay. So I take this one and I get du is equal to, du 1 over u is equal to dv. And then so again, my substitution, the du thing, and now the two heads of integration. If u is equal to x, this x over here, if u is equal to x, then it means that v is equal to log of x. Okay, substitution from the rule. Now, if u is equal to 1, it means that v is equal to log of 1, which is 0. Everyone understands how I apply the substitution? Okay. Now I literally just plug it in. And what do I get? I get integral from, careful with the heads of integration, log of x, 0, 1 over u times, 1 minus v du. Again, careful. U and v in the same fraction, two variables, this is not okay. So what can I do here? I can just write this as integral log of x, 0, 1 minus v times du over u. Why did I write it like that? Because as you said, when you have du, when you see this thing, you just, after you have a little bit of experience, you just see that, hey, it's just going to cancel out really nicely with this thing. This is just integral log of x, 0, 1 minus v d of v, which is really beautiful. Okay, because what do we know about? What do we know about 1 minus v, or in general? That's just a log. So this is just a log of, with a minus, 1 minus v dv. So this is just equal to 1 minus v, from ln of x to 0. So this is just equal to, as I said, minus ln 1 minus 0 minus another minus here, ln 1 minus ln of x. Minus with minus becomes plus. This is 0, so this is just plus ln 1 minus ln of x. Okay, everything that I did after this is sorry I did it like in an ugly or whatever manner. Everything that followed should be clear after the substitution. This was the key part. This or this, obviously both work. They're the same thing. Substitution was the key part in solving this problem. Okay, that choice, that decision that just randomly came in basically solves your entire problem. Now, let's do the other case. And I don't like this problem because I think you really can't go wrong with it. In the sense that any substitution you work, I think it's going to work. Literally all of it. Okay, what's the time? All right, I'll give you 2 minutes to choose your substitution because I already spilled it out. I should have said it's for using I don't know, something else. Oh, actually, I rephrase that. You can solve it by parts again as well. You can solve it however you want it to. I'll just give you 2 minutes. You choose your weapon and try to write something to solve it. Okay? It's literally as simple. And this is, I think, a perfect class example because it really can't go wrong. Like, really, it just works out however you flip it. Oh, sorry, that's a parentheses. It's ln. I'll rewrite it again. Sorry. Integral EV ln square brackets 1 plus EV squared close square brackets dv. At least I think that's the one, right? Yeah, that's right. Okay. I'll give you like a couple of minutes. And then we're going to solve it before the break. And then I'm going to teach you something that sounds really smart, but you probably learned in third grade how to do. So that's going to be exciting. Okay, any ideas? Any ideas how to solve this? Yes. Open the parentheses. So you said, right, this is basically 1 squared plus 2 EV plus EV, everything squared, and then have the EV as U? Maybe, but I have a simpler way to do that. Like if you want to do that, what is log of A squared? It's just 2 log of A. So before you make any decisions on what to use and whatever, I don't know if it's good enough for you guys, but for me, it makes sense to take the simplest steps to simplify. Every bit of advantage I can get, I will take it. to get some intuition to where I want to get. So what do I mean by this? This is log of 1 plus EV squared. So I just write this as 1/2 integral EV 2 times log 1 plus EV dV. Okay? I just use this rule. That's my first start. And I get rid of this. I would think that's pretty decent. Okay? Now, substitution. Can you make it work? Yes. Is it gonna be easy? No. But it does work. Like every solution, if you're really diligent on it, will work here. The one I would use is, again, for substitution. For substitution, the one I would use would be log of 1 plus EV. Why? Again, ugliest thing, want to get rid of it. I have no other ideas. I tried the ugliest thing. I wish I had like a formal mathematical explanation, but it's just what it is. Okay? It just builds on intuition. Now, will this give you a solution? Yes. Will it be easy? No. So, I would think, like, I'm just trying to get you an idea of what's going through my head. I see this problem. I first try to make it as simple as possible, give myself all the advantages I can get. I see this. I think, okay, log ugly. I would think of substitution. Does this work? Maybe. Then I think, what else do I know? By parts. And here, remember, and by parts, I need to choose my which one is derivative, which one is not derivative. Remember, I never want to integrate log, so I'm just going to say, okay, let's just assume my A prime, because I can't use U and B because it's confusing. My A prime is EV, and my B is log of 1 plus EV. Okay, so I think about it for a second. I let my head flow around it, and then I'm like, I write some sketch. And I'm gonna use the by parts because I think it's easier and simpler. Okay? It just works for me. But this is what went through my head. I simplified as much as possible, and I identified my possible strategies. What can I do to this? What do I know to do with this? And these are the only two solutions that came to my head. If none of these work, then it is what it is. I just move to the next one. And I come later when I have a better idea. But this is what I had as an idea. So any questions on this? Any ideas? Okay. So if A is this, then A is equal to integral E of V dV, which is just E of V. And this, I have derivative of B respective of V, and this is just 1 plus EV times EV. This is, again, pretty nice, looks pretty good. And then what is the by parts is the following. It's A, B is equal to integral of A prime B plus integral B prime A. Does this ring any bell? Looks familiar? Hopefully. It's the same formula, just instead of UV, I use this thing. Okay. So now what do we get? Let's see. From here, I get A, so EV, times this thing over here, EV1 plus E to the power of V, plus, equal, sorry about that, equal to integral. What is it's this one. It's EV here times 1 E plus V EV D of V plus the last term is just my, sorry about this. Sorry. I completely messed up. Sorry about that. I completely messed up. So this is my B, this is my A, this is my A prime, this is my B prime. Sorry about that. Completely messed up. What can I say? See? Happens to the best of us. No problem. I just go again. So A is just e to the power of V. B is just log of 1 plus EV. This is just A prime EV times B log of 1 plus EV, D of V. And this is my fraction where I started, plus integral B prime. This is 1 plus EV E of V times EV dV. That's a lot of V's there. Okay. Does everyone understand how I applied the by parts here? Does it make sense how I did it? Okay. I think I did the same exact way I always do it. I didn't change anything outside of the notation. Now, let's see where we're at. This is done. There's nothing for me to do there. This is what I started with. So I just need to solve this thing. So my integral is just equal to minus this integral, which looks like I have no idea how to solve, but I actually do. Okay, so why did I put integral? This, oh, yeah. So this is the integral I want to compute. This is done, so I just need to compute this thing. What is that equal to? EV1 plus EV times EV, EV. This is just equal to integral 1 plus EV times EV. Does my writing make sense to everyone? This thing is just equal to this thing. So I just use that. And now I'm left with some wonderful, wonderful terms, because this is equal to integral, split this up, EV times 1, if you want, minus E of V, 1 plus E of V, dV, split it nicely, and I get integral EV, D of V, minus integral EV, 1 plus EV, dV. This is trivial, e to the power of V. And this thing, what a surprise, we already did that, right? Isn't this just the derivative of log of 1 plus EV, derivative with respect to V? So this is just, this thing is that. So my integral is just EV minus log 1 plus EV. Okay? Yeah, so just to wrap things up, my first, okay, I just want to show the idea, because the computation is not, oh, this is the final end. Yeah, the idea is that the computation in itself, you shouldn't, I'm not hoping that you get my computation right now. The computation is not important. Okay? I can't follow, sometimes it's hard for me to follow your simple computation. I'm not expecting you guys to follow my computation. What I'm expecting you guys to understand is how to tackle such a problem. If you don't know how to start it, you're never going to finish it. If you know how to start it and you work on it, you're eventually going to finish it. That's my way of thinking. So the idea is you started by looking at your thing. You simplified it in a nice way. I mean, the simplest you could do. And then you just have ideas floating through your head. If you have ideas, it's a good sign. It means that you are able to solve it. If you test all your ideas, you're able to solve it. If you have no ideas, that's when it sucks, because you don't know where to start. Okay? So I'm just hoping that the best I can do in terms of teaching you guys integrals is giving you a start. Other than that, I can't solve it for you. Nobody can solve it for you. As I told you, integrals require practice. But my duty is to give you a start, to tell you how to start a problem. So you have this thing over here and you're stuck. You don't know what to do. So you just circle ideas. You have substitution, might work. I don't know. And then you have by parts. These are the only two methods you've learned. These are all the ideas I have. If it doesn't work with these two, then I just blame the professor because I didn't learn anything else. Simple as it is. So I just had the idea. I don't know. I tried by parts first in the sake of time. I would have tried the substitution as well. Doesn't matter. And this by parts application is, again, the standard procedure. I'm 100% sure if you would spend 5 minutes and write that by parts in your own notation clearly on your paper, it wouldn't seem hard at all. Okay? So the idea is I chose by parts. Remember, it was a hard choice between A and B, basically, which one is derivative, which one is the non-derivative. That was the choice in the by parts. And we use the fact that we never want to integrate log of 1 plus EV. You never want to integrate that alone. It's never going to give you something nice or workable. So that's why I took the derivative of log. I took B as the no derivative sign, and then I computed the derivative of it. Okay? That's kind of the idea. And then it was just pure computation, which I'm certain all of you, if you spend 5 minutes, you could do the computation. Okay? The important idea is how to start. What's your choice and what you can do to solve the problem. Let's take a break right now. If you have any questions, I'm here. Hey. I just fell out in this part. Yeah. Yeah, it's where the oh yeah, right. Okay. You got it. Oh, this one. Whoa. With this one, there's never going to make this one out there. I'm just going to just yeah. This one, I just did that next thing. You just break the thing down with this. It's hi. Oh, I just thought it.
One plus you just multiply and divide with 1 plus.
No, I just keep trying because I thought it makes my integration process easier. I could integrate this. I thought this was much more. For the first, I think that that's what so you're saying I did it wrong? Maybe. Yeah. It's not the first one. You are very. Oh, you just looking at the paper? Oh, that's true. Oh, that's true. That's true. That's true. I mean, yeah, that's true. Yeah. Yeah, but it's just, yeah, that's true. So I'm saying I did it wrong that day. Maybe, I don't know where. Maybe. What is that? Like, what do you mean by that? One second, let me just, mute this. It might be, it might be. Okay. Okay, so. Okay, guys, hopefully it was, we did the exam. I hopefully it wasn't that hard, at least the logic behind it. Again, it's really hard, and whatever problems I would do here in front, it would be hard for you to follow because just how it is. I can't follow somebody else's computation. You can't follow mine. Makes sense. But the idea is to not panic and have possible solutions that you can explore in the exam, because you have time. Time is not an issue. The issue is that you waste half an hour just staring at it and not knowing where to start. Okay. Hopefully I'll give you the start. Now, there's one topic which has been covered in the last couple of years. I've not seen it on the exam, but I don't know. I'm just gonna show it to you guys. I hope it's really fast. It's not really stressful. So hopefully it will show something. What do you do when you have fractions of the type x to the third plus 3x squared plus 1 over x plus 2 dx? What do you do with this type of things? Say again, sorry. That is correct. If it was a limit, I would give you maximum points and tell you, yes, this goes to infinity. Now this is an integral. So you telling me that this is really big or the upper top is bigger is not gonna help me. But yes, if this is the limit, it will work out. I'm gonna teach you what is called, in a smart way, polynomial division. Before we go into that, let's take the simplest case. How do you divide 647 by 11? Come on, everyone remembers this. So I think this goes 5 times here, and you have 5, and there's a 9, 7 here. And then you'd have 8 times, and you get 8, 8, and you get 9. Okay, come on, I don't need to show you this. Everyone knows this. Now, the idea is that we're going to do the same exact thing we did to this number. We're going to do the same exact to this polynomial up top. Okay, follow me up on this. Remember, same exact logic, just for like, I don't know, 10 years later or something. So I have x squared plus 3x squared plus 1. We divide this by x plus 2. Okay, everyone follows? Just look right afterwards. I promise I'll give you time. So we take the biggest power first. This is x squared. I take x squared. So I have x squared times x, that's x to the third, plus 2x squared. Okay? Now what do I get? This is 0, and here I have an x squared plus a 1. What do I have here? X squared plus x. I get it again, and I get x squared plus 2x. When I divide, I get minus 2. This goes 0, minus 2x plus 1. Okay, I do it once again for the last time. X minus 2 minus 2. This becomes minus 2x minus 4 equal to 5. When you don't have when the power of x here is smaller than this, you stop, similar to how you stop when 9 is smaller than 11. This is polynomial division. Why is it called polynomial division? Because I can just write my x to the third plus 3x squared plus 1 is just equal to x squared, x plus 2 times x squared plus x minus 2 plus 5. No, because you're subtracting. It's plus 1 minus 4. So that's 4. We're just subtracting in every case. This is minus that, etc., etc. Just like we're doing in the simple case, we're just subtracting. From 64, I'm subtracting 55. From etc., etc. Everyone understand what I'm doing here? Okay, this is what is called really formally in the math books polynomial division, which is basically just dividing numbers like we learned in the first one. Now, why is this writing? Why do you need to do polynomial division? Why does this work out? Let me show you why it works out, and then we're going to take some more examples, okay? Why does it work out? Well, I had to compute this integral, which is ugly. X squared, 3x squared plus 1, x plus 2 dx, right? And I just use this replacement. Integral x plus 2, x squared plus x minus 2, x plus 2. And I just take the 5 out because I don't like it. Okay? I just replaced my x to the third, this thing. I just replaced it with this thing over here. Okay? Now, why is this writing really, really strong? Because this is equal to, I simplified this. This is equal to integral x squared plus x minus 2 dx plus integral 5 x plus 2 dx. And now you can see these ones look much, much nicer than everything else because this is just equal to x third over 3 plus x2 over 2 minus 2x plus 5 log of x plus 2 plus a constant. So this is why polynomial division works. It only works when the power above the line or the power in the denominator is greater than the power in the denominator. So I have 3 here, 1 here. So it's a good place to apply polynomial division. Now, let's take another example. You do it yourself. Let's see if you can divide, and then I will divide here. Let's try integral x4. I'll give you x4. You can handle it. 2x4 plus 7x the third minus 2x squared plus 1 over x squared minus 3x dx. Well, just try to divide this the same way we divided the other thing and see where we get. If you ever forget how to do this, just think of it exactly how you would do it when dividing two numbers. I know you've used only a calculator since you were born, so you forgot how to do that, but hopefully it helps. Okay, so how we're doing on the division. Let's see if I can still divide. Okay, everyone just watch what I'm doing. 2x4 plus 7x the third minus 2x squared plus 1. Divide this by this x squared minus 3x. Again, the way you do it is you just compare the bigger powers. I look, x squared, 2x fourth. This is going to give me 2x squared. Okay? And I get 2x fourth minus 6x to the third. I don't know who said that, but really well. I applaud that. Okay, now, what do we get after the first division? This goes away, so I have 13x to the third minus 2x squared plus 1. Again, same thing. Check the biggest power, how many times it gets here. That's 13x. What do I get? 13x to the third minus 39. That's a lot of x's. X squared. Okay? What do we have? This goes away. This goes away. I have minus plus, so that's 37x squared plus 1. I can do one last alley-oop. How many times x squared and 37x squared? Just 37. So this is 37x squared minus 111. I think that's correct. 111 x. This goes away. This goes away. So I have 111 x plus 1. And I stop because x squared bigger than x. Everyone understand what I did? Is it hard? Like what I'm basically doing here? I'm just dividing the polynomial because it makes such a difference when computing the integral. So again, yeah. Let's go again over what I did. So I know I'm given this integral, okay? And I notice there's a higher power here compared to here. This means I can quote unquote divide these things. So I just proceed like I did in the 3rd grade or something when you learn division. This, and let's do it simple. This is 2x to the 4th. How many times x squared? That's just 2x squared. Multiply it, and I get 2x 4th minus 2x squared times 3x, 6x to the 3rd. This goes away, and now I have 7x to the 3rd. This is a minus 6, so that's 13x third minus 2x squared plus 1. Good. Now, same logic. X squared, 13x to the 3rd, that is 13x. And I get 13x third minus 13x times 3x, 39x squared. Minus, that's plus. So I get 37x squared plus 1. X squared, 37 times. Minus 37 times 3, that's 111, as far as I computed. X. And that's kind of what I have left. Minus plus 1. And I'm done. This is the remainder, I think it's called. So now, what did I prove with all these divisions? I proved that the polynomial that I started with, 2x fourth plus 7x to the 3rd minus 2x squared plus 1 is equal to x squared minus 3x, 2x squared plus 13x plus 37. Okay? Plus the remainder, plus 111x plus 1. Okay, good. Now, my integral, 2x fourth plus 7x to the 3rd minus 2x squared plus 1 over x squared minus 3x dx is equal to, I just plug in this, I plug it in. And I get integral x squared minus 3x. I just copy everything just to make it simpler for you guys. x squared minus 3x dx. Okay, and after I do this, I think this is supposed to be 111. Anyway, okay. Now, what I like to do after this, I just like to split everything. I don't know, it just works for me. So I get integral of x squared minus 3x, 2x squared plus 13x plus 37, x squared minus 3x dx plus integral 111x over x squared minus 3x dx plus integral 1 x squared minus 3x dx. Everyone followed to this point? Now, why is this notation so strong? Again, because this only ugly term just becomes like the simplest thing in the world. That just goes away. That is the whole idea of division. That I'm just simplifying stuff. Okay, and this is just integral of 2x squared plus 13x plus 37 dx. And now for the rest of them, they're easy to compute. You can do literally whatever you want to them. It doesn't matter. I'm actually not going to compute them because I'm not really interested in them. Plus, I think you should be able to do it. Okay. What I wanted to show you is how we can simplify those huge powers into just something simple like this, which everyone should know what it is, and then some fractions which are usually just ln of that stuff. Okay, that was the main idea why I wanted to show you polynomial division. I guess I don't know. We can do like another example. Can we do an exam problem in 10 minutes? Probably. But it might be a little bit fast. So let's see if we can find a simpler one. The simplest one in the world. Okay. Oh, this is a good one. I could give you to divide more polynomials, but I think you got the idea by now how to divide polynomials. I can just create any polynomial and divide by any polynomial. So I think I would just be partially making fun of you guys, just giving you harder polynomials to divide. I think once you get the idea, you can divide anything by anything. It's pretty simple. But now, how about this integral? Integral from 1 to x e square root of z dz. How does this work? This is a great problem. It does give you the idea to substitute. So maybe it's not the nicest one, but you'll be fine. You'll be fine. It's good to just check ideas. Sometimes it's good to do hard problems to see if you have the ideas, if they just come to you, because you got to imagine that on the exam, if they don't come to you, I'm not going to be there to whisper them in your ear. You got to create them something, and that only happens for practice. So yeah. On the second part, I'm not even gonna we're not gonna have time to actually solve this and let you think about it. So I would rather just end our, I guess, 5 minutes early or something. And if you promise that you're gonna spend 5 minutes on this integral, and then tomorrow we start with ideas how to solve this. Okay? Do we have a deal? All right, so let's just end the class right now. I'll see you guys tomorrow.